Okay, so today we will continue to talk about the interesting optics and imaging. Okay, especially we will go beyond ray optics. We will go to the wave optics, and then we will see the direct benefits of imaging if we can understand the wave optics. Okay, especially using the wave optics, we can gain two advantages. One is we get more dimensions. We can use the properties of the light to look into the biological system, get more insights from different axes. That's one. Second one is using the wave optics. We now can understand better what is the theory, what is the theoretical basis of resolution limit, and then how can we figure out a way to break that limit. Okay. So can everybody see my screen? Can you see my screen?
Yep.
Yeah.
Okay, very good. Let's get started. Good. Okay. So regarding to the logistics, this Friday we will have really exciting talk from Dr. Anna Porras. She will talk about the microbe and bacteria in the human environment, the human body microenvironment. This is really exciting topic. She is a faculty member in the biomedical engineering. Okay, so feel free to ask questions during the lecture. And then after that, we will have our final presentation. All of you will give the presentation, show your upgraded project report. Okay, so then it will be December 4th and December 6th. So we look forward to your presentation. Okay, and let me know if you need me to recommend, add new comments to your proposal or to your slides. I'm very happy to do that. Okay, so feel free. Yeah, good. I hope this process will let you learn how to better design a project, write the report, and present your science. Okay, good. Okay, so now let's get to the wave optics. So we finished the ray optics. So from ray optics, we understand how the images are formed from the sample plane to the imaging plane, right? How the image get formed after the after rays of the light pass through lens, pass through the transparent optical elements. Okay, and then but only this ray optics, those theory cannot explain all the observations people find in the nature. Okay, so then to expand our knowledge of the optics, we also need to learn the new properties of the light. That is, light is not only a ray. Ray optics actually means that light is consistent of the particles, consists of photons. But in the same time, people gradually realized light is also can also display in a way like a wave. Okay, and then especially that wave is electrical magnetic wave. It's not one wave, it's two waves coupled together, electrical wave and magnetic wave coupled together. Okay, so that gives us more insights of the light, and then it can be used to explain many new phenomena, such as why the light can have interference. If they are just consisting of particles, then they will not be able to generate interference, right? And then if we can understand the wave better, to know the nature of the wave, we find that we will appreciate that the light also has a polarization. Okay, so all these phenomena can be very well appreciated and can be used to we can engineer them to explore new biology. Okay, and then finally, after the discovery of green fluorescent proteins, people start to realize those fluorescent protein or those light sensitive protein. Okay, all those protein actually can be engineered to become the interesting samples or interesting tools to interact with light, and then we can use that to probe the the cells or living multi-cell living systems, right? So all those three topics actually are combined together. We will go back and forth, all three of together, beyond the just the ray optics. Okay, so to start, as we mentioned before, in the first part of the ray optics, we said that when we have when people put a opaque board in front of a lamp, in front of the lighting object, and then make a hole there, they will find at the back of the opaque board, we will see an image. We will see an image of this real object, and then that is actually the initial evidence that the light travels in the straight way, right? And then that give rise to the idea of the ray, light ray and the light particle, right? But then people find that if you further play with this experiment, you will find something very strange. This pinhole, this hole here, if you make that to be smaller and smaller, then the amount of light goes through this pinhole, become little less and less. So this image become dimmer and dimmer. When this pinhole become too small, then the object, the image of this image should become very, very dim, and that is the extrapolation of the idea that the light goes like around the straight line, like the rays, right? So that is the extrapolation. However, when the people did the experiment, they find that when this pinhole becomes small enough, it not only let the image become dimmer, but also make this image to be bigger, to make this image to be even bigger than the original image. Okay, so that's something very strange. It cannot be explained by the theory that the light always go like in a around a straight line. Okay, so from that time on, people think that the light may not. We may just observe the one face of the light. They may have different faces at a different restriction, different condition. The new faces start to emerge. Okay, so the founding scientist to make the progress in answering those puzzles actually is Dr. Christian Huygens. He is a very talented scientist. He is a Dutch mathematician, astronomer, physicist, and horologist. Okay, horologist means the watch, making a watch. Okay, different types of watch. So he is the person firstly realized light may not be only consist of particles. So the light consists of particles is actually raised by the Newton. Okay, so Newton has a theory called the corpuscular theory. Okay, he said Newton claimed that light is consists of particles, because Newton, you remember Newton's law, three Newton's law. At that time, Newton is very, very good in analyzing the motion of objects around the direct lines. And then he, based on the Newton's law, he derived the momentum, potential energy, kinetic energy, right? So all developed by Newton. So when Newton used those established theory, those theories established by himself, when he applied those theory into the light, he find many of his theory still valid. So then he become more and more convinced light is consisting of the particles, and the light is and those particles compose the light rays. Okay, but this theory cannot explain many phenomena, including the one I just showed in the previous slides. So then Huygens developed the new theory. He thinks light actually also consists of can display in the form of waves. Okay, so then it becomes two schools of thoughts. Okay, first school is there is a when the light travels in the media, it actually, if we look at it in the micro or nano scale, this actually has a flux of particles. Okay, so those particles, each one is called a photon. There are many photons go in the same time. Okay, and then by you following this plan, people did many quantification and then find the light speed and the energy of the light, okay, and the frequency of light. So they find all this information. And in this school, Newton is the leading one, but also Planck and Einstein. Planck is the Max Planck. Okay, he is the founder of quantum mechanics. So remember the idea of the particle, right? This each photon is quantum, right? Each one is quantum. So Max Planck and Albert Einstein, they all belonging to this school. But later on, after initially, these two scientists belong to this school of thoughts. But afterwards, they also realized light has the dual nature. So it's dual nature, dual particle and wave nature. Okay. Another school is the wave. Is the idea of the wave. So that is led by the Huygens and then Maxwell. He is the founder of electromagnetic. Right. He developed the Maxwell equations. Right. And also the Hertz. Right. So those two schools actually coexist there. Okay. They actually complementary to each other. Okay. So if we think about the light like a wave, then after many decades of investigation, people find light, even the visible light. Okay, I'm not saying the microwave light or the classical electromagnetic light like in the radio. I'm not seeing that light. I'm seeing the visible light. Okay, so the wavelengths between 400 nanometer to 800 nanometer, invisible, the visible light. Okay, so for those light, actually if you measure the electric field and the magnetic field, you will find these two fields are coupled together. Electric field is much stronger. Magnetic field is weaker, but still exists there. Okay, and then these two waves form transverse wave. Okay, means the propagation direction. So in this around this arrow, this is a propagation distance, propagation direction. If the propagation direction is perpendicular to the oscillation direction of the wave, then this is called a transverse wave. So in this case, for the light, actually it is composed of two transverse waves. One is electrical wave, one is a magnetic wave, and then they are in the same phase. Okay, they started at the same origin point. Okay, if the wave is a longitudinal wave, not transverse wave, that means the oscillation of the wave is in the same direction of propagation direction. Okay, that is one example is the sound wave. When we talk, the sound, when the sound propagates from the mouth to our ears, actually it goes through the propagation, and that propagation is carried out by the longitudinal wave. Okay, so this is the nature of the light. Okay, the wave. Now, if we look at and then this wave can be written in an equation called C equal to lambda mu. C is the light speed. That we know is 3 times 10 to 8 meters per second, right? So this is the high speed, and then lambda is the wavelength from the first peak to next peak. Okay, first positive peak to next positive peak, and then mu is the frequency. Okay, now if you look at one subsector of the wave, just one piece, either the electrical wave or magnetic wave, just pick up one, and then you conceptualize it, then it looks like a sine wave, right? You can model it like a sine function, right? And then within the sign function, we can define what is the wavelength, what is the peak, what is the where is the peak, where is the valley, and then from peak to the valley, we know that is 2 times of the magnitude, right? And then from the magnitude, if you multiply the magnitude, square magnitude, you get the intensity, right? In the light, our eyes or the camera chip is not measuring the amplitude, because amplitude always change. Amplitude is keep changing. The absolute maximum amplitude is the same, but the real magnitude is changing as a function of time. But our eyes is not doing the differentiation. Our eyes is, and as well as the camera chip, they are doing the integration within a certain time period, right? So then it integrates those intensity, those amplitude change. That actually is the multiply amplitude, and then that becomes the intensity, and it becomes the brightness of the pictures. That is what we perceive, okay? And then also here, from this model, you can also see the frequency, right? Frequency, and as well as its inverse, the period, okay? So that's the characteristics of the wave. That's we already know in the basic physics, but this model can also be applied to the light. All the light also follow this model, okay? And at the beginning of the class, as I said, once we realized the light also behave like a wave, then we actually can look at this physical signal from different axes. If the light is behaving like the wave, then it can have the property like diffraction, can have the property of interference, can have the property of polarization. All 3 of them are very important. Very important properties of wave. And then they all can be engineered to become different types of imaging system, different types of microscope to look at the biological samples. For example, this diffraction. Do you guys hear me?
Yes. Yep, we hear you.
Okay, good. For example, this diffraction, the reason in the first few slides when we shrink the pinhole, and then we see the image become blur, become dim, and become larger, is because when the wave pass through the pinhole, that has the size, has the diameter at the similar level of the wavelength. This is wavelength at a similar level of the similar spatial level of the wavelength. Then the light will diffract. Okay, then they will become wider. Okay, we have a video in the next few slides, and you will see that. So then this is called diffraction. That will cause the image to be larger. Yeah, and also when we use the microscope to look at the samples, as we mentioned before, we can, if you don't have any special treatment, then you use your microscope. You use the best objective you can purchase to look at the sample. The smallest feature you can see is about 250 nanometer, okay? So that is also because of diffraction. You will see that in the next few slides. If you want to see the things smaller than that size, using only the light is not sufficient. You need to combine with other technologies, okay? Also interference, that's very important. Also polarization, also very important. I think I showed you some pictures of the muscle, right? Of the muscle picture that was imaged by polarization microscope. Because in the muscle there are many motor protein complex. They are assembled in the periodical manner, spatially periodical manner. Those kind of structure can be easily captured by polarization microscope without any staining, without any labeling. Okay, that is the best. So you can see the structure, periodic structure, very well in the polarization microscope. And then in the nature, actually, in the cell, many structure are periodically changing, like the DNA. DNA is a double helix, right? But if you look at that, in the helix is continuously repeating, right? So those kind of structure can be imaged using the polarization microscope. Okay. Now, now for the wave, if you look at the light as a wave, for the 1D wave, it has a spatial temporal distribution. So here on the y-axis, vertical axis is the temporal distribution. At different time, this wave, how long distance it propagate around the z direction, around x direction. Okay, around here I see a z direction. Now, so at the t equal to 0, this wave looks like this. Okay, and then if you go a half of a quarter, t equals t divided by 8, eighth of the t, eighth of the period, then this wave moves rightwards, right? Moves this distance. So you see that from this peak to this peak, okay? And then continue as the time progresses. It moves more, like here, moves more, like here, moves more, up to here. When the t equals to period, then it pass through 1 lambda distance. And then this wave, the new wave, when you take a snapshot, here imagine you take many snapshots. When you take a snapshot at a t equals to one period, the picture will be the same as the t equal to 0, because this light they periodically, cyclically repeat itself, right? If we look at so this is just one wave, right? One wave. But when we encounter the light in the nature, they are actually not one wave. There are many of those waves combined together. Especially, you can summarize all kind of light wave into 2 cases. One kind of case is called plane wave. So you have the light going in one direction, all the light, all those. So you imagine this one, you have many of this one parallel to each other within the same phase, parallel to each other. And then they all go in one direction. Then all of them added together is like a plane. And then each plane is a one phase of that wave, of that many waves. Okay, one phase. They're all within the same phase. So then they go like a plane by plane. Another one is called a spherical wave. If the light going out in an angle, okay, then from the center on, they are gradually expand the wave front, and then they form each circle here, each surface, spherical surface here, consists of the wave of the same phase, okay, and then they continue to expand. But in the same time, if you look at if the light is traveling like a spherical wave, then based on the principle of energy conservation, the amplitude of the light becomes dimmer and dimmer. Okay, so becomes smaller and smaller. So then because the intensity covered by those space, so intensity per area or per volume becomes lower and lower, right? Because the total energy is the same. Now the volume becomes bigger and bigger. Okay, so these 2 cases are most conventional, most common light wave propagation cases. For any complicated optical design, you can conceptualize them into many combinations of those 2 cases. Okay, so if you look at here is more figures and descriptions of these 2 cases. Okay, so for the plane wave, the different time point and different spatial locations, the wave will propagate in the same direction and remain the same phase. For the spherical wave, the phase of the light remains the same on the spherical surface, and then as they propagated, the occupied volume become larger and larger. Okay, so these 2 this is the different image representation of the same ideas. Okay, now if we look, if you look back, by the way, those slides I have uploaded into the Canvas, so you can watch them. Okay, so this is another representation of the two wave propagation cases. Now, these two cases, in fact, they can be integrated together. They can be combined together to be one. For example, if we have one light source, one particle, one fluorophore, it generates light, and then the light emitted out in all directions. You see here the many different rings, right? Those rings you can imagine it this way. The black one is the lowest intensity region. White one is the highest intensity region. Okay, so when the light coming out, they actually form the wave. They form the wave up and down, many of them. Okay, so this one on the left hand side, this is a spherical wave because the light is coming from a point. And then once this light propagated for enough distance at the far away location, this the front of the wave will become planary. Then those spherical wave actually converts into planary wave now. So these two are the same now. Okay. This case is a light coming out from the point. It is also valid in the reversed way. If we have a planar wave come in and then concentrate into one point, then the planar wave can be converted into a spherical wave, right? This case we actually see many times. Both cases we have seen many times. First case is like a 1 point. If you have 1 point source, a fluorophore sitting on the sample specimen plane, and then you emit light, generate a spherical wave. And then if you want to make this distance to be shorter, then you can simply put a positive lens here, microscope objective. Then you can convert the spherical wave into the ray, right? Into the ray that in the idea of wave optics, that is the planar wave, right? So this process is converting spherical wave to the planar wave. Or if you have the light, a ray of light coming collimated in a collimated form, encounter a lens, then the lens can focus the light into the focal point. That is the second case. The lens is converting the plane wave into spherical wave, right? So this is the case we have observed, we have seen for several times now. Okay. Now, yeah, here is actually the picture showing that idea. Now you have a spherical wave, and then it can be converted into planar wave by the lens. Okay, and also in the same time, if even you don't use the lens, if you have a crystal ball, you have a transparent object, elliptical shaped material, it can also convert the incoming planetary wave and then focus them into one point inside of the crystal ball. And then that also convert the planar wave into spherical wave. Okay. Now go back to the question we asked before. When I explained this before, that when we do the imaging, when we image the point, we place many different lenses in the microscope and then convert the sample into an image and an image to another image, right? Again, relay this. Now, I mentioned this before, that the point after they get imaged into the imaging plane, it actually is not a point anymore. I mentioned this before, right? So why is that? That is because if you look at this point, the focus point, you will find there actually is not a point. It's actually a finite. It's called waste like this, waste of the beam. Okay, so in fact, this is a focal point after lens. When the lens converge the collimated beam and focus then into a point, it actually generate a wrist, and this wrist has its own diameter, its own depth. Okay, and this diameter actually can be calculated. It can be expressed in this equation. Okay, so in this equation you will know this W is not 0. It has a finite value. For the visible light, this distance is always hundreds of nanometer. Okay, so it existing there. In this wrist looks like this structure. It is not a point. It allows the light to go through, but it's not infinitely small. It's not a point anymore. Okay. So in the last lecture, we talked about we showed the focus, defocus, converge, and diverge in the idea of ray optics. Now we can replot that diagram in terms of the wave optics. So then it looks the process is actually initiated from the wave, from the spherical wave, and then converted into plane wave. Okay, so here is the position. This is the position, right? This different position. Here is 0, the different position, and then after they get converted by the lens, it converted into the angle now, right? So this angle is not 0 because this point is not in the 0 point, so it go up, then the angle go down, right? So the plane wave, and then this plane wave get focused by another lens and then converge into the point. So the planar wave converted into a spherical wave, right? And that spherical wave, after passing through this point, they diverge again, and then converged by another lens, become planar wave, and then another lens become spherical wave again, and then focus on the imaging plane. Okay, this is the process. This is the process in the imaging system. Okay, and then and then here is the figure shows the wave properties. I have all those slides in the canvas. You can see more details there. In the class, I hope to explain to you the very, very important key point first, and then let you appreciate that using the idea of the wave optics, what kind of phenomena can be explained, what kind of new engineering method can be developed, can be invented. Okay, that is our key point in the class. Yeah. Also here, this is the characterization of the waves. Okay. Now, if we look at the light as a wave, another important property you will find useful is the light actually consists of different frequency. The light have different frequency. Okay, so at those different frequency gives different energy of the photon, because the photon is each photon the energy is h mu. H is the Planck constant, the constant developed by the Max Planck. That's constant. Mu is the frequency, and if the frequency is larger, then the energy is also larger. Okay, in the visible light spectrum, the high energy part is actually the violet from the violet on, and then gradually decrease indigo, blue, aqua, green, yellow, orange, red. So the energy actually decrease. This energy is proportional to the frequency, linearly proportional to the frequency, but inversely proportional to the wavelengths. Okay, so as the light become more and more red, wavelengths gradually increase, energy gradually decrease. Okay, that's actually that's the reason that when we do the imaging of the biological sample, or even the glass, okay, the red light, or the light with a higher wavelengths can penetrate through those samples deeper. That's actually the reason, because those photon those red photon, they have a longer wavelength and a smaller frequency. Their photon has a less energy be carried there, and they are less likely to interact or to excite the electron in the samples. They will not excite the electron in the glass, in the human body, in the animal body, in the cells. Okay, so then they will not get interfered. So then they will go past deeper. But in the other hand, those violet photon or blue photon, they actually carry high energy, so they can easily excite the electrons in those samples, and then they will fight with them, and then they will forget their mission to go through the sample, and then they keep fighting there and generate heat there. Okay, so that's actually the reason. So based on this, based on the property of those photons, you actually yeah. So here is here is we put the light into an even bigger picture. Okay, so this is the visible light. If we go beyond this spectrum, you will see the light with the even less frequency and even higher frequency, means even higher wavelengths and even lower wavelengths, right? So all those are different electromagnetic waves. Light belongs to one part of that. Okay, light is a subset of electromagnetic wave. Okay, so yeah, so here's another picture showing in the energy diagram what's the corresponding energy of those photons. Yeah, this figure actually explain what I just said about the factor that a longer wavelength light can penetrate through the samples better. So here, two figures. First figure on the left shows the absorption of the light as a function of the light's wavelength. Okay, so this x-axis is the same as here. So x-axis is the wavelength of the light from 200 nanometer to 180 nanometer. Okay, so here the set attenuation coefficient means how much light get attenuated. This attenuation is because of the scattering and because of the absorption of the light. Now, if the light has a short wavelength like 200 or 600, they actually have a high attenuation coefficient, means they actually can be absorbed more. Okay? When the light frequency becomes more than 600, this region, then the attenuation becomes much lower. Here they show different material, right? Oxygen, the blood, that is we have a lot in the body, and oxygen and deoxygen the blood, and also skin and fat. All those things combined together become our tissue, right? And then if the light want to penetrate deeper into the samples, then the light have the wavelength in this region can better penetrate, and then we can allow us to see more information in the sample, right? And then this is for the light's property on the left hand side. Right hand side actually is the current technology, camera technology. So there are this is a material of the camera chip. You can see that for the camera chip, this is a semiconductor physics. People find that those light sensitive material, that they are actually become more sensitive to the light. They become more sensitive to the light. Means they have higher quantum efficiency. Okay, they are more sensitive to the light that have the longer wavelengths. Okay, so this means they can better sense the light with the red color. Okay, that is the implication of this diagram. This is a good thing. Means the current solid state physics technology actually can match with the light properties in the biological system. This means that if we want to image the tissue, we do better to use any reagent, any fluorophore, any tools that emit the light have longer wavelengths. Okay, and then at the same time, we use the camera, we use the current existing camera to capture their information. Okay, so that's actually a good thing. So this actually open the door for the deep tissue imaging. Okay. Also, also if you look at also because of the wavelength, the frequency difference of the light, then if you have the combined light feed into the lens or feed into the glass material, they, depending on their frequency, they actually have different refractive index. So the refracting index we write before, they actually can be furthermore categorized depending on the wavelength of light. Okay, usually the larger frequency light, they have a larger refractive index. Okay, those are also used for properties people use to image in the living system. So all those properties I talked about here right now is not just a simple description in the basic physics class. They actually now in the graduate level class, you can actually think about how to use them to obtain new insights in the nature. Okay. Okay. Now that's all for the wave part. I want to switch. Let me switch back to another part. Based on this knowledge, I want to explain to you the resolution part even better. So let me switch to another PowerPoint slides. Do you guys see my new shared screen?
Yep, we see it.
Okay. Now, at this point, we have appreciated light is also a wave, right? We also appreciate that. Now, in the rest 5 minutes or so, I want to show you that what is the results? What is the results that induced by these wave properties of the light? Okay, one result is the resolution. Okay, so yeah, here actually is the replay of the how the wave propagate between the sample to the eye. Okay, after going through the lens. Here, there's a very important concept called a point spread function. Point spread function, PSF. This is very important. What it means is, this is the function. What it means is, when there is a point in the real nature, when we use our eyes to see the sky, in our eyes, it actually is not a point, because of the reason we explained previously. There are a lot of light lost there, right? So the wave cannot effectively interfere with each other. So what we observed here is something else. There's a question mark in our eyes. Okay, that is something else. This something is called a point spread function. It actually is the image of this point, but this image is not a point anymore. Okay, so that this actually is this kind of thing is not a point anymore. This factor can be explained by the wave optics. So in the Huygens' idea, when he developed the wave optics several decades ago, he actually think that when the light propagates like a wave, on the light wavefront, each point is capable to serve as a new source of light, new source of a spherical light. So each point can generate a new wave. And then all of them generate a new wave at the same time on the same wavefront. And then this small spherical wave will interfere with each other and then propagate forward. Okay. And then each point here is called a wavelet. Okay. This is the word you always hear in the signal processing field. Okay. And also in the optics field, because they are connected together. Okay. Now here, this picture only shows a few wavelets. for example. But in Huygens' idea, you actually have a lot of wavelet around these lines. Okay. Now, and when he talk about the interference, what he means is you have two kind of interference. One is a constructive interference. If the light two wave they are in phase, means they at the same point they have the same angle there, same phase there. Okay, and then these two waves added together, they actually can make the resulting wave to be even more violent. Okay, so that's called constructive interference. But if the two wave mismatch about the pi, about the half wavelengths, then they actually combine together. They actually can cancel each other. That's the destructive interference. Okay, so Huygens' idea is there are many wavelet can be generated on the wavefront, and then they will produce both constructive and destructive interference throughout the space. In the place we do not see any image, it's not because there are no light. It still have light. It's just that they have the destructive interference. We don't see that. Okay, that is his the core of his wave optics idea. Okay, now from there, of course, here this is the effect. From there, you can understand many things. Here is just the example of two wavelet. If there are only two, so from this wavefront, if we only pick up two wavelet, then because this is a spherical wave, so they will go to all the places. But if we look at the different places, we will see the phase interference from these 2 points actually are different, because they are influenced by the distance, right? Influenced by distance, different distance, they have different phases. So you see that at this point, they are added together, okay? Because the net change of these two distance is integer times the wavelength. So then this point they have the constructive interference. But go to another position, you have the destructive interference, and then go to other position, you again have a constructive interference, right? So this actually, if you do many of these wavelet, you will know that how the pattern looks like. Okay. Now in the real image, here you can see this. We have a lens here. Okay. After the sample get after the particle on the specimen plane emit out the light, their light will also generate this wavefront. And then this wavefront will concentrate the light to one point, right? To one point. That is a ray optics. But if you think about the wave optics, this wavefront will generate many overlap that result in many overlap around this line. That is resulting from many wavefront, many wavelet on this wavefront, right? You will have many of this. Now let's see how that happens, how that generate the point spread function here, and how that influence the resolution of the microscope. Okay, so now let me go to there. Here, this you can read in the slides. Now, most important thing is here. Most important thing is here. Yeah. Now, if we have the turbulence here, okay, we have turbulence here, and then we have a sample plane here. If we have on the sample, after the light goes through this lens, they will generate this wavefront. If we pick up only 5 points here, do the simulation, each point is a wavelet, and then they will send out the wave. And then if all of them interfere on the imaging plane, on the camera chip, then they will generate this kind of pattern. If 5, okay? If only 5 outer wavelet. If you increase it, if you have more, okay, then you will find the center point. This is a focal point. Center point become more and more stronger, more and more brighter, and then other part get receive more destructive interference, become less now. Okay, become less now. Okay, now if you have all of them, you have all of the wavelet here generated, let them send out the light to generate the image here. Then you will find something like this. You will find something like this. Okay, center part is very bright, other part is less bright, but you still have some residual fringe there. Okay, those residual fringes because here this wavefront is only part of the light from the original sample. If you collect all of them, and then you let the interference on the sample plane, then you will exactly get that point in the nature mapped to the point on the imaging plane. You can get exactly that. Okay. Now, this is the best. This is the best we can get, and this one is called a point spread function. It's a PSF. The PSF. Okay. Anything when you do the image, you actually the image, any sample, any cell, any sample, they have many of those particles inside. What we are doing is every point in the sample in a cell goes through the same process, and then generate their corresponding point spread function on the image plane. You generate that. Okay. So it's another real cell to the real cell image. Okay. And this point spread function actually, the way it can be theoretically calculated, it actually is generated by doing the convolution calculation. We discussed the convolution before in the context of diffusion, but in the optics, it also uses the convolution. Those lengths, each length is actually doing a convolution plus Fourier transfer, so that you can get this point spread function. Okay. Now, if remember we talked about the idea of a numerical aperture. If the size is larger of the aperture, right, the angle is wider, you actually have this longer wavefront, right? Then you will have more wavelets around this line, and then it turns out the final interference pattern in the imaging plane actually become brighter and become narrower. If you have the numerical aperture that is very small, so angle is very shallow, then you will have less wavelet there. And then it turns out the center part, the patterns on the imaging at the center part actually become wider. This is actually not good. If you want to see the details of the particles better, you want its image to be narrower. Do you guys hear me?
Yeah.
Yep. Yeah. Okay, good. You actually want this pattern to be narrower because this one is image of one particle. What if I have another particle very close to it, and then it also fall in very close to it in a cell in a sample plane, but once they are imaged to the imaging plane, it's a very wide, very broad those pattern. Then these two very closely will contact with each other. They looks like very contact each other, but in reality is separated. So then that means that in the microscope, I cannot tell apart by my eyes. I cannot tell apart these 2 points. I will think these two are the same point. That's not good, right? We want to see the details between these two things, right? That idea is called resolution. So if you have a higher numerical aperture, you actually can get a thinner image. Then you have a higher resolving power. Okay, that's what we want. Now, this resolving power not only depends on this numerical aperture, but also depending on which light we use. We just mentioned that the light has different wavelengths, different frequency, and a different refractive index, right? We just mentioned that. And those factors actually play the role during this interference process. If the light has a smaller wavelengths, higher energy, they can generate thinner patterns. That's better. Okay. And here is actually a diagram showing different spread point spread function generated in the same optics, but for different wavelength light. Then you will see this one is the best. Okay, this purple one is best. And then if you go longer wavelengths, you see the point spread function become larger. So that will cause trouble for us, right? Now, I don't have time to talk about all those very exciting things. We're actually doing the research in the lab. So if you have an interest in the future, I can tell you the details, very exciting details here. So I just want to show you one example here. Let me show you two examples here. So, oh, by the way, this one, what is this? This actually is the light pattern within at a focal point. So if you have the light focused there, it actually is not a point. It actually has a different interference pattern there. So this is a pattern. This is a pattern. Okay. And then, as I said, if you use the best optics, largest numerical aperture and the smallest wavelengths you use, you go to the best. What you will get is the 2 points in the imaging plane. The best you can get 2 points is this value, 0.61 lambda divided by NA. So if we have 2 points in the nature, in the imaging plane, what we will see is 2 points like this. We will see 2 points like this, and their distance is described by this equation. Okay, by this equation. Now, using this equation, if you put the lambda, the wavelength in, put the numerical aperture in, the best one you can find in the nature, your best one you put in, this number will give us about 200 to 250 nanometer. 200 to 250 nanometer. You cannot be zero. Okay, so that means if you have two images, two particles, they are even closer than this value, then you will see blurry things. Even these two spheres become even closer. Then we will not be able to tell this is the 1 point or 2 points. We cannot tell. Okay. For example, here is one example. Oh, this is in the XY plane. If you look at the Z plane, they also cannot tell. Okay. So let me give you one example. Here is one example. We just change the numerical aperture. If in the nature you have the points like this, okay, many points. Do you guys see my mouse? Do you see my mouse?
Yeah.
Yeah.
If you in the nature you have you have 4 points here, okay, in the nature. Now, in the nature they have 4 points here. Then you use a very good microscope, high in NA, and then the low wavelengths and the best immersion oil. Then in the imaging plane, what you see is like this. You have 4 points. Yes, we have got 4 points, but they have many rings there. The ring I also see, that is the uninterfered wave, right? I also see that. So this is the image I get. But if you use a microscope has lower quality, then what you get is this. You find the separation of the particle become harder to tell. Let's actually follow this equation. Follow this equation because your NA become lower now. Your NA become lower. Then lambda divided by NA, right? NA is in the denominator. Lower this number, this distance become larger, right? Larger distance. Then, this one lower and they become larger. Then you means that the critical length I can tell become larger. Means your resolution becomes smaller. Okay. Then you get this kind of image. And then if you use even lower NA, then even harder to tell them apart now. Okay. So if you use this one, you will think here I only have 1 point. But in fact, if you increase the power of the microscope, you will gradually see that 4 points. Oh, yes, indeed, they have 4 points, right? You will see that. And also you will find, oh, there are even smaller other points there, right? So this is the resolution. Now I just finally show you 1 point to give you this is just several particles. If you look at the image, how the resolution change. So here, this is a one image if you take by a low quality camera, okay, you look at this, you will not know what it is, right? Do you guys see my mouse?
Yep, we see it.
Yeah.
So we cannot tell what is this. That means our resolution is very low. Resolution very low, although we can tell the color, okay? But resolution very low. We don't know what it is. Now you gradually increase your resolution. Then now you start to see something. You further increase it, you will further see it. And then further, you will see this, okay? And then further, you will see this. And then if you increase even further, you will see even better. Even the small stripe here, you can see that. And then even further, this you can see much better things. So that is the resolution, okay? Now, if you go back to the point I just mentioned here. Just mention a point, this point. I saw a question. Okay, Laura, you go ahead. So here, I mentioned that no matter how you change those parameters, you still have a limitation. It cannot become zero, right? I mentioned that. So that means that we cannot get to the best of the tiny feature in the samples, right? So once you encounter that situation, you need to use non-optical ways. Use non-optical ways to find it out. One way is you can use some physics laws, some chemistry approaches. Then you can look into those particles one by one, and each one you can pinpoint their position, and then find another one, pinpoint that position, and then recombine them together into the computer. Then you can see the details of each particle's position. Okay, that is the basic idea of the super resolution microscope. Okay, so we use those in the lab all the time, and in the future, if you guys have questions, we can always discuss this. Okay, I can always show you those methods. Okay, right now it's 4 p.m. I need to stop here, and feel free